My name is Darby McMillan, and today I will be reviewing our new refrigerant guide with you. This PowerPoint is an overview of a PDF document we created as a reference guide for refrigerants. Understanding these refrigerants is important to evaluate the environmental impacts that these chemicals present, as well as potential regulatory impacts you might face. We created this document as a single point of reference to save you time doing several internet searches to find the information you need. The primary information we cover is refrigerant safety group and global warming potential. Refrigerant safety groups, which designate toxicity and flammability, are defined in ASHRAE Standard 34. The capital letter A or B designates a toxicity class based upon allowable exposure. Class A denotes refrigerants of lower toxicity, and Class B denotes refrigerants of higher toxicity. The number, meanwhile, indicates flammability. The three main flammability classifications are Class 1 for refrigerants that do not propagate a flame when tested per the standard, Class 2 for refrigerants of lower flammability, and Class 3 for highly flammable refrigerants such as the hydrocarbons. ASHRAE recently updated the safety classification matrix to include a new flammability subclass 2L for flammability Class 2 refrigerants that burn very slowly. Some of the new HFO refrigerants are mildly flammable and are classified as A2L. This indicates that they are of lower toxicity and have low burning velocity. This chart summarizes the information in the previous slide as a quick reference tool for refrigerant safety classifications. Global warming potential, or GWP, is a measure of how much a climate pollutant affects global warming. GWP 100 measures the impact a gas has over the course of 100 years, using CO2 as a benchmark. For example, 1 ton of R134A released into the atmosphere is equivalent to 1,430 tons of carbon dioxide. This is just one of many refrigerants that are thousands of times more polluting than CO2 alone, as you can see in the chart. This is important information to have access to as the high GWP refrigerant phase down is already underway. Globally, the Kigali Amendment was enacted in 2016 to begin the phase down of high GWP refrigerants. The Technology Transitions portion of the American Innovation and Manufacturing Act, or the AIM Act, authorizes the EPA to phase down production and consumption of hydrofluorocarbons, HFCs, in the United States by 85% by 2036. The Significant New Alternatives Policy, or SNAP, established under the Clean Air Act, allows the EPA to evaluate substitutes for ozone-depleting substances and hydrofluorocarbons. In this chart, released by the US EPA, you can see that refrigeration and air conditioning is projected to contribute about 12% of global non-CO2 greenhouse gas emissions by 2030, which is why these regulations are being put into place in our sector. Informational tables constitute the bulk of this reference information for this document. Sorted by refrigerant type, they provide a single place to view pertinent information. The safety and flammability ratings are based on ASHRAE 34. Global warming potential, or GWP values listed in this document are primarily from the Intergovernmental Panel on Climate Change. Most values are from the IPCC AR4 report published in 2007 and the AR6 report published in 2022. This data was specifically chosen to mirror the values used in the SNAP and AIM Act legislation. In 1928, the first chlorofluorocarbon and hydrochlorofluorocarbon refrigerants were created and came into popularity as the first generation of synthetic refrigerants. Several years later, we realized that the CFC and HCFC refrigerants deplete the ozone layer, and in 1987, the Montreal Protocol was finalized, beginning a phase-out of these refrigerants. By January 2010, in the United States, there was a ban on production and import of R22. We have the CFC refrigerant chart on this slide, and the HCFC chart on the next. Moving on to the hydrofluorocarbon refrigerants. HFC refrigerants were introduced in place of CFCs and HCFCs as they have no ozone depletion potential. However, the issue is that they still have a significant global warming impact, typically thousands of times worse than CO2 alone. These refrigerants are currently in the process of being phased out of production and use. Hydrofluoroolefin refrigerants, or HFOs, are considered fourth-generation refrigerants made of hydrogen, fluorine, and carbon. They have no ozone depletion potential and very low global warming potential. HFOs, however, do not always have the desired refrigerant characteristics and require compounding with HFCs to be effective. We'll go over refrigerant blends in the next couple of slides. Another issue is that HFOs degrade into forever chemicals, including trifluoroacetic acid, or TFA, which has been found in drinking water in the US and Europe, may harm ecosystems and human health. One of the biggest refrigerant sources of TFA is HFO 1234YF. It's most commonly used in car air conditioners. Azeotropic refrigerant blends are mixtures of two or more compounds that evaporate and condense at the same temperature. Therefore, azeotropic blends act like pure substances. As previously mentioned, many applications HFOs do not have the desired characteristics and require compounding with HFCs. One of these is R513A, a blend of R1234YF, which is an HFO, and R134A, which is an HFC. Zeotropic refrigerant blends are mixtures of two or more compounds with different boiling points. In a process known as refrigerant glide, zeotropic blends will evaporate and condense over a range of temperatures. Therefore, this chart also lists glide for each of these refrigerants at both low and high pressure conditions. Hydrocarbon refrigerants are compounds composed of hydrogen and carbon, typically byproducts of crude oil. Examples of hydrocarbons used in cooling systems include propane and isobutane. These refrigerants are very efficient and have very low global warming potential. However, high flammability is a concern. You'll notice these are all A3 refrigerants. Lastly, natural refrigerants, specifically ammonia and CO2, are energy efficient due to their thermodynamic properties. More than that, natural refrigerants are safer for the environment. They have little or no global warming potential and no ozone depletion potential. Therefore, all natural refrigerants are future-proof and will never be regulated out of the refrigerant market.